Learning Vision, Language, and Action, an Analysis of Embodied or Interactive Question Answering, by Gireesh, Suresh, Chrish, Maxey, and me, Jack Rasiel. Overview. So what is embodied question answering? Well, in embodied question answering, an agent is posed a question about its environment, for example, what color is the car, and must explore and possibly interact with its environment to find an answer. This is a recently proposed and rapidly developing research area, combining elements of visual question answering and deep reinforcement learning. We'll examine two papers, both released in the past year, which are representative of this field. One is Gordon, Daniel et al. IQA, Visual Question Answering in Interactive Environments, and the other, Das and Abhishek et al.'s Neural Modular Control for Embodied Question Answering. A note on terminology: Gordon et al. Call this problem interactive question answering, Das et al. Call it embodied question answering. For this presentation we'll say embodied question answering when we refer to the problem in general, EQA when talking about Das et al.'s dataset, and IQA when talking about Gordon's. So why embodied AI? Embodied question answering isn't an end unto itself. It's a stepping stone on the way to higher functioning artificial intelligence. Das et al. States it aptly. The goal of embodied question answering is to build intelligent agents that can perceive their environment, communicate, so hold a natural language dialogue grounded in the environment, and act. This is a fundamental scientific goal in AI, and even a small advance towards it could fundamentally change our lives, enabling everything from assistive dialogue agents for the visually impaired to natural language interaction with self-driving cars, in-home smart personal assistants, and more. For our presentation, Gireesh will introduce some of the philosophical motivations behind this research. He'll also give an overview of some of the recent research which is closely related to embodied question answering. These papers provide an interesting contrast. They introduce different datasets based on different virtual environments and with different kinds of questions, and propose agents with different designs. Chrish will explore these datasets and detail how the agents are designed and trained. Both papers perform a series of experiments with their agents. They, of course, benchmark their agents' question-answering performance on their datasets. They also run experiments tweaking aspects of the agent's design and training to better understand how different components affect the agent's performance and behavior. I'll detail what these are and discuss the implication of their results. I'll also analyze future directions for both projects and for the embodied question-answering problem as a whole.
Now, moving on to the motivation, we have it inspired from the human psychology. Now basically, everybody will be familiar with maturation, which is nothing but the biological growth process that enable orderly changes in behavior, relatively uninfluenced by the experience. Everyone has a growth rate and are affected differently, but we share the similar growth tendencies. For example, first you roll over before you sit, then you sit before you stand, then you stand before you walk, and walk before we do dance. Now, ideally, we wish to develop the cognitive skills as we grow. These, in specific, refer to the think, learn, and communication which we humans do with others. One of the most important person in cognitive psychology is the wonder kid from Switzerland, Dr. Jean Piaget. He has a PhD in zoology and he has done his work in psychoanalysis. The main question he had addressed was, how does knowledge grow for human? He proposed certain things to explain this. In specific, Dr. Piaget proposed that as we grow, we create something called as schemas, which will help us get a basic yet sound framework understanding of certain aspects. Concepts ranging from what is a bird, what is a house, and so on. We get all these things from the concept of schema. We also learn a lot more about abstract things like love, friendship, and betrayal. Not to forget that we strive constantly for cognitive equilibrium, wherein we get harmony between our thoughts and our environment. This is achieved through two processes listed in the slide. Assimilation. This is the interpretation of information in terms of existing schemas. Example, a baby sees a deer but has been taught or which it has not been taught or which is not aware of. Then here the agent tries to map the deer with a known entity, that is a horse. In short, the agent here tried to fit with the understanding of what it has learned earlier. Other hand means the agent tries to adjust the learnt schema and fills the missing gap of understanding, if any. The example for this would be the same baby from the previous instance. As it grows, that is, as it learns, is able to differentiate between the various horse breeds and tell which is the black beauty or white beauty, wherein the sole detection of horse was not possible earlier. Continuing with the motivation from psychology, I would like to show the correspondence or similarities that is observed from the 1700s to the current day's deep learning. For this, I consider the 4-stage theory of cognitive development. Stage 1 is the sensory motor stage. Here, we basically experience the senses and learn some of the major senses like touching, seeing, grabbing, hearing, and listening. A kid will learn the notion of right from the very instant when they trip or fall down and remain cautious henceforth. The similar concept which we see in deep learning is perception. In specific, the perception can be classified into active and passive perception, wherein active deals with lidars and ultrasonics and passives deal with certain other sensors like light and pressure sensors. Also, we could say that deep learning also uses detectable drivable area, free space detection using concepts like semantic segmentation. The second stage that is analogous with deep learning are as shown. Here we consider object permanence from psychology. The example for this would be throwing a blanket over a toy, and a baby might think that the toy has vanished, but then the toy is still there and it is just out of sight. This can be explained as the awareness that things may exist when out of sight or when they are out of the field of their view. The same analogous concept in deep learning is the object detection, wherein we try to figure out how many apples or how many objects of anything which is there in a particular scene or a frame. Example would be the basic detection of objects, and the advanced versions would be detection of cancer and wound, which is now possible with the deep learning algorithms as listed there. The third stage would be reversibility, which is nothing but the concept of measure of shape or the color equivalence at different scenarios. An example of this would be the concept that a ball of clay smashed into a flat thing can be rolled back into a ball. Though such concepts might be hard, eventually we tend to understand them based on the experience and the learning. An analog concept in deep learning here would be the common sense reasoning that is used by intelligent systems which uses AI. For example, if you ask a robot where is a milk can, probably the agent would look at the refrigerator and then figure out to open the door. The next question would be similarly on asking where the cars can be found, wherein the agent tries to navigate to a garage by opening an exit door. The fourth and the last complex stage in the psychological chain would be operational stage, wherein the human agent has learned to reason based on logical thinking, abstraction, and finds proofs that attest the claimed belief. The very equivalent concept here would be language grounding. The real world has semantic regularities. For example, home layout tends to follow certain conventions like the hall or the tries to be closer to a living area so that you can go and grab a snack. These information can be leveraged by the robot in deep learning to improve the planning process. The same thing is being discussed later in the presentation as we go about the base papers as well. Now moving on to the related work done by previous people in this era. The first one would be visual question answering, wherein we use vision and language to tackle the problem of question answering for an intelligent system. The language here refers to a single shot question answering, which is typically done using a one-hot vector. Here, for example, in the image shown, we have asked certain questions of what sign is this, and this can be converted to a one-hot vector stating a sign, and similar concepts we used to follow the same procedure. The lack of control here compared to the other slides, compared to the other work, is that the robot is given access to only a selected image frame. This can result in dilemma when you need to track an object over a sequence of images before you can answer any given question. The second one would be visual navigation, which uses the power of vision and action of a robot. Here, a specified agent is given or driven to a goal based on reward functions or explicitly conditioning goal state representation. In the image shown, if you see, the robot is taking the current frame and the image from the next frame and generates a differential map with which the planner is being fed to about the action, whether to go straight, turn right or turn left or anything accordingly. The next related work would be situated language learning. Here, simply put, the globally perceived environment is being assumed based on a preconceived notion based on the floor space that the robot have access to. Here, we can see from the image that the dining room is approximately situated closer to the living room and the outdoor rather than a garage. And the same pattern continues with the other images as well. The concept can be leveraged for planning in the robot and can be used as well. The next paper which we considered for the project is Embodiment, which is basically embodied question answering system. Here we use vision, language and action concept to tackle the problem. Here we perform a less complex task. For example, go to a position X in terms of a 2D game, or go and follow a maze based on a templated instruction in the scenario of a 3D environment. These kind of tasks are performed here based on something similar to a realistic data, which we call the House 3D or the AI Thor 2 images, which we will be discussing later in the slides. If you can see the image, the robot is posed a question of what color the car is, for which the robot has to navigate through the environment following a set of actions, and then had to find the car, for which it had to perform a certain set of planning actions, and later had to come up with the answer that the car is of orange color. The next related work which we are going to discuss is interactive environment, or based on the graph, if you could see, it is nothing but the video question answering system. Here we consider the input as video, which is nothing but set of frames of images in a sequence. The data here is broadly classified into two categories, one being the 2D world, which uses the dataset of X world, and the second one is a 3D world wherein we use AI Thor 2D, which is a custom dataset that is being developed, and the images of these and the further explanations can be found in the slides to come in the presentation.
Thanks, Gireesh. So next we'll talk about methods, including the environments and datasets, as well as agent design and training. So as is prevalent today, simulated environments are often used to train agents. This is in place of, as a pre-training step, real-world environments, which are often at best costly to train in and at worst infeasible or dangerous. If an agent, for instance, will end up colliding with obstacles often during training, this is really not feasible and can be quite dangerous given a real-world environment. So there are a variety of simulated environments available today, a few of which are DeepMind's Lab, which is a tweaked version of the Quake engine, providing a very rudimentary maze structure with various objects within the maze that can represent positive or negative rewards. Next, we have House 3D, created through the Sun CG 3D models. This is an environment representing a variety of rooms with 80 plus objects in the rooms, and essentially represents a house in general with potentially multiple levels. Next, we have the AirSim environment, which is a plug-in for the Unreal Engine. The Unreal Engine is a common game engine that can create a variety of environments with a variety of fidelity. And the Unreal Engine acts as a plug-in, providing a quadcopter or a car, as seen here, that can interact with the environment. And finally, we have the AI2 Thor environment, which is a near photorealistic rendering of a variety of indoor rooms, including a multitude of actionable objects. So in particular, we'll be focusing on the House 3D, SunCG, EQA V1 dataset, and the AI2 Thor iQuad V1 dataset. So for the EQA V1 dataset, there are a large number of scenes, 45,000 in total, quite a few objects, 80 plus labeled objects, 20 plus room types. Each object has instant coordinates, RGB image frames, semantic segmentation and depth frames can be extracted from the environment, and simple physics are available. The AI2 Thor environment, on the other hand, has a far number less available scenes, 120 in total, roughly equivalent labeled objects, 80 plus, near photorealistic rendering, especially compared to the House 3D environment. And although not explicitly mentioned, due to the fact that it is a 3D environment, there is potential for segmentation and depth rendering. One of the key differences here with this data set is the fact that many of the objects are actionable, which means that they are movable or interactable in some way, as well as some objects can act as containers, such as a refrigerator containing a coffee mug. The rendering and the physics engine is within the Unity engine, another gaming engine, and both datasets are considered balanced datasets, which means that the questions asked from the datasets are asked in a way such that there is not a biased, trivial answer that the agent can learn. For instance, answering yes to a question is right 80% of the time. Next, we'll discuss the hierarchical ideologies that are present in both of these models. In general, an agent needs to have some sort of structure in order to interact with and learn a semantic understanding of its environment. Without this, it is relatively hopeless for the agent to, in any meaningful way, answer a question. So, in general, an agent needs to make a overall high-level plan. This can include some number of steps, and these steps can be low-level actions such as turn left, move forward, and eventually answer the given question. These low-level steps can be passed to a low-level controller, which then can enact these steps. Of course, in real life, there's many more complications, including the need for memory, maps, and many low-level controllers, all of these feeding back on each other. So let's focus first on the IQA model. As seen here, there are a variety of modules within this model, including a planner as a high-level controller, a semantic memory that keeps track of the map the agent is exploring, and various low-level controllers, including a navigator, manipulator, detector, scanner, and answerer. First, we'll discuss one of the main contributions from this paper, which is the global semantic memory. This essentially is a map of the environment, keeping a variety of features per pixel in the map, including object detection probabilities for each pixel, an occupancy grid, and the potential for exploration for each pixel. For instance, is the robot likely to explore that area, or has it explored it already? This large map is fed piecewise throughout the exploration to a GRU, and in particular, the navigator has write access to this map and provides local inputs to the GRU, combined with the local area within the map and those local inputs from the navigator. An update to the map is created and passed back to the global semantic memory. Seen here is the planner for the IQA model. In particular, this takes an image and the previous step for each time step, and this is passed to the GRU cell, as well as features from the semantic memory, which is passed through a CNN, and the question embedding. These three outputs are concatenated together and passed through a fully connected network, which then provides various probabilities for actions to take, as well as the value of those actions. And in particular, the planner invokes the low-level controllers. So for instance, this is the navigator controller. This takes the occupancy grid of a 5x5 area in front of the agent, as well as relative to the agent, and within that occupancy grid, the location the agent wishes to travel to, and the current image the agent sees. This outputs a shortest path via A star to that location provided, as well as an update to the global semantic memory, and a termination signal that, when having reached a certain threshold, returns control back to the planner. Next, we see the detector, which actually uses pre-trained modules, particularly YOLO v3 and FCRN. YOLO v3 for object detection, FCRN for monocular depth estimation. And these provide the agent with perception of the environment, allowing it to actually move and navigate throughout it. And then lastly, we have the answerer module. This takes the image as well as the semantic memory concatenated with a tiled version of the question embedding, and it passes these through a CNN and eventually a fully connected network, which then predicts probabilities over the various answers that the agent has available to it. Thus, the agent is able to actually answer the question in a more intelligent way. The two modules not mentioned in particular are the manipulator and the scanner. These are fixed modules that do not require learning, and essentially have predefined actions to interact with the environment. Next, we'll discuss the neural module control for visual question answering. This also has a high-level planner which takes in CNN image features and question embeddings from LSTM layers. And this goes to low-level steps. However, instead of these steps being low-level controls as seen in IQA, this model actually predicts sub-policies such as exit room, find object, and in this case answer, which is still the same. These sub-policies are then broken into low-level steps that can be enacted by the agent. This ends up looking like such here with this map, in which case an agent might start in the bedroom, and the high-level policy determines to exit the room, find the living room, and then find the fireplace, given the question, where is the fireplace? Or is there a fireplace? Okay, so as is often the case with reinforcement learning, the domains of the agent's environment can be quite large. For instance, if the agent were to require learning how to detect objects, learn a map, depth map, learn navigation policies, as well as answering policies all at once, this is a very high dimensional domain and can complicate the learning efficiency, time, and overall accuracy. So there are a variety of techniques that one or both of these papers enact in order to rein in the domain in some way. First, we have the hierarchical structure that we just discussed. This allows the learning to be broken into stages or to various parts that can be trained separately, as is discussed here. There's also pre-trained modules that the IQA paper in particular uses. For instance, the YOLO v3 and the VCRN networks already have trained weights that can then be fine-tuned on the given data sets. This saves time and improves accuracy. Then we have isolated module training with fine-tuning. So each module can be trained with a gold standard or an expert signal separately from all the other modules. This allows for each module to learn with a clean signal instead of the messy signals from the other modules trying to learn as well. Once each module is pre-trained, they can all be put together and trained together with fine-tuning. So next, these visual question answering tasks in general have a sparse reward structure. For instance, the reward comes from, did you answer the question right or wrong? So in order to combat that sparse reward structure, intermediate rewards are often placed within the environment as well for the agent. For instance, progress towards the goal, the percentage exploration of the environment can be positive rewards, and a negative reward might include collision or time spent in general trying to answer the question. Then we have auxiliary tasks that can be learned by the agent. In particular, the IQA utilizes this. As seen in the paper, Learning to Navigate in Complex Environments, it is seen that auxiliary tasks that are supervisory can help act as a separate reward structure for the agent, helping to shape the internal representation of the environment and ultimately helping the agent to achieve the goal of the reinforcement learning quicker and more accurately. In particular, in IQA, the agent learns to predict per time step not just which action to take, but also of all the actions, which ones are feasible or not, given a specific time step. Then we have the reinforcement learning technique used by both models. This is A3C, a common reinforcement learning technique that provides faster RL as well as more accurate results in general. And finally, we have limited actionability. So neither agent has full continuous action within their respective environments. For instance, in IQA, when an agent turns left, this is by 90 degrees, not any number of degrees. So with limited actionability, the agent actually is restricted within the environment towards what it can actually explore and do. Next, Jack will discuss the experiments and the analysis of the results.
Experiments and analysis. Among the questions these papers ask through their experiments are, how does the agent perform on their EQA or IQA dataset? How do various design elements impact the behavior of their agent? How does tweaking their training regimen affect agent performance? And how does their agent generalize to previously unseen environments? Let's look at how the agent in IQA performed on that dataset. Gordon et al. Benchmarked their agent, HIMN, Hierarchical Interactive Memory Network, against a human and a baseline system. The baseline is a common architecture used in related work in reinforcement learning for visual planning and navigation. It lacks HIMN's semantic memory and federated low-level controllers, and is trained purely with reinforcement learning, instead of imitation learning and RL. HIMN outperforms the baseline significantly on accuracy and reaches its answer in fewer steps. Notably, the baseline performs even worse than random chance. The authors reason that because there's no explicit immediate reward signal for remembering object detections, the baseline never learns to do so. HIMN's semantic memory module, on the other hand, forces the creation of a persistent memory of objects in the agent's environment. This allows the agent to learn an association between object detections and questions. The baseline agent also never learns to effectively explore its environment, while the HIMN agent is encouraged to go forth and populate its semantic memory. Now let's look at NMC's performance on the EQA dataset. Their methods are slightly different. First, in addition to question accuracy, they also measure navigation. Because their tasks all involve finding a single object, they can modulate task difficulty by spawning the agent at different distances from the target. They evaluate their agent's performances at 3 different distances, given as the number of step actions, 10, 30, and 50 steps from the target object. This is shown in D0. Focus on D delta, though, because that's where the change in distance to the target is shown. They benchmark against Pac-Man, the system proposed in the initial EQA paper. Their agent, NMC, Neural Modular Control, beats the baseline's accuracy by 3 to 4%, and ends closer to the target for more difficult tasks. They attribute the improvement to the abstraction of primitive actions to submodules. This enables the master policy to operate over longer time horizons, which is critical when the rewards are so sparse. They also explore performance impact of using reinforcement learning, which leads naturally to our discussion of ablation analysis. Both papers modified designs and training regimens to gain a deeper understanding of how those designs influence the system's behavior. For example, what effect does fine-tuning with reinforcement learning have versus just training via imitation learning? NMC explores this, testing both NMC and the baseline with and without RL-based fine-tuning. They find that reinforcement learning significantly improves performance, especially for NMC's answer accuracy. They also examine this for the subgoal modules, experimenting with training using only imitation learning, BC, the green curve, only reinforcement learning, the orange curve, and a combination of the two, in pink. Imitation learning is more sample efficient than reinforcement learning from scratch. Reinforcement fine-tuning greatly improves performance over imitation learning alone. While imitating expert trajectories provides dense feedback for how to take good actions, it doesn't expose the agent to mistakes. Fine-tuning with reinforcement learning fills that gap, allowing the agent to interact with its environment, make mistakes, and then learn how to recover from them. In IQA, Gordon et al. Examined the performance effects of various submodule tweaks. They replaced the visual navigation submodules with ground truth, that's rows 2 and 3, finding each substitution boosts performance considerably. They also try omitting the question vector from the planner and find that performance decreases significantly. It's perhaps unsurprising, but confirms that the planner is indeed paying attention to the questions and using it to inform its behavior. Lastly, they test a system without using the lost on invalid actions. This causes a massive performance drop, even with ground truth for navigation and vision. They analyze invalid actions further, showing just how important they are to training. Failed actions are due to navigation failures, failing to see an obstacle, or interaction failures, trying to interact with something too far away or otherwise impossible. It's important to note that the agent is always penalized for taking an invalid action, but the action loss is provided for every action. Comparing column 2 to the other columns, we see that the invalid action loss reduces the percentage of invalid actions by nearly an order of magnitude. One important takeaway is that the invalid action loss is crucial for mitigating the difficulties of the agent's large action space and enabling faster and more effective learning. EQA and IQA differ in important ways. For example, they pose different questions to their agents. EQA only asks about the properties of a single object, while IQA asks questions about potentially multiple objects. This informs the design of their respective agents. EQA's NMC agent is designed to find an object, and then answer a question based on the last few frames seen before the object was found. IQA's counting task requires an agent to undertake an open-ended exploration of its environment until it's satisfied that it's found all instances of the desired object. IQA's AI2Thor-based environment allows for interaction, which further complicates actions and tasks. NMC's high-level planner is also more interpretable than HIMN's. Compare NMC's subtasks, exit room, find room, etc., to HIMN's, which is, navigate to a target coordinate relative to the current location. However, it remains to be seen whether NMC's approach can scale to more challenging tasks. HIMN's semantic memory is limited in the kinds of spatial relationships it can represent. The semantic memory is organized as a 2D grid, meaning that it can't encode 3D relationships, such as the one object being on top of another. Gordon et al. Propose to expand this in future work. Both papers propose a number of future research directions. For example, they propose expanding their relatively simple language models to allow for questions to be posed in natural language. This could mature into a very interesting research direction, exploring how the agents can ground natural language in their environments. Currently, their questions are posed simply and unambiguously. What color is the car? Consider the complexity induced by a dataset of questions like, is there a red fruit in the kitchen? The agent would have to learn to place objects in higher-level classes, and this would also complicate the design of the agent's internal representation of the world. Could HIMN's grid-based semantic memory be expanded to represent this new complexity in a meaningful way? EQA proposes to add counting and spatial relation questions, which, as we've mentioned, would necessitate a major change in their agent design. EQA v2 would also ask questions involving more than one object. For example, is there a piano and a couch in the... We'd also like to see the environments themselves made more challenging and diverse. What if instead of 80 objects, the environment contained hundreds or thousands? It remains an open question, though, how these agents will adapt to increasingly complex tasks and environments. As we've seen, the main challenges in training these agents are the complexity of the action space and the sparsity of rewards during training. Longer and more complex tasks will certainly require new innovations in agent design to make them tractable.